My dear students, let me welcome you to the General Revision edition of Physics. In this edition, you'll be encountered with miscellaneous questions. The questions will be of gradual increase in difficulty. Hopefully, you'll find them interesting and beneficial. So let's get started. Write the scientific term. The magnetic flux which induces an EMF of 1 volt in a single turn coil, when the flux is reduced, flux through the coil is reduced to 0 in 1 second. What is the scientific term? Okay, it is the Webb. Okay. Magnetic flux density of a uniform magnetic field which produces a force of 1 Newton on a wire 1 meter in length carrying a current of 1 ampere when the wire is placed perpendicular to the field. Magnetic flux density, okay, which produces a force of 1 Newton on a wire 1 meter in length carrying a current of 1 ampere and the wire is placed perpendicular to the field. Of course, it is the Tesla. The instantaneous EMF, instantaneous electromotive force induced in the coil of an AC dynamo when the plane of the coil, okay, makes an angle 45 with the field. What about this instantaneous EMF? It will be equal to the, yes, thank you very much, effective value. It is the effective value of the induced EMF. The resistance of a wire, 1 meter in length, the wire is 1 meter in length, having a cross-sectional area, 1 meter squared at 20 Celsius is 1.7 times 10 to the power of negative 8 ohm. Okay, what do you understand from this? Okay, so resistivity must be equal to 1.7 times 10 to the power of negative 8 ohm meter. Resistivity of the material of that wire at the mentioned temperature is 1.7 times 10 to the power of negative 8 ohm meter. The torque exerted on the coil. Torque exerted on a coil when the coil is placed such that its plane is parallel to a magnetic field of density 1 Tesla, the torque is equal to 0.08 Newton meter. Okay, so magnetic dipole moment, okay, of the coil is 0.08 ampere meter squared. Scientific term, okay, an EMF of 2 millivolt is induced in a coil when the current changes in the coil at a rate of 1 ampere per second. EMF of 2 millivolt, so inductance is equal to 2 millihenry. Ratio of the electric power or electric energy produced in the secondary coil to the electric power consumed in the primary coil of a transformer is 0.9. Ratio between the two powers, produced power and consumed power. It is efficiency. Okay. So efficiency of the transformer is 90%. We can say, okay, efficiency of course equals VSIS over VPIP, and it is 90%. Scientific term, the direct current that produces the same heating effect per second as that produced by an alternating current is 10 amperes. Direct current which produces same thermal effect per second is the effective value. Effective value of the AC current is 10 amperes. The rule which determines the direction of the current induced in a coil, the moment the field through the coil, the moment the field that intercepts the coil changes. Okay, which rule is used to determine direction of the induced current in a coil? It is Lenz's rule. And now we've got another type of questions. What happens when? What happens when the two metallic rings in an AC dynamo are replaced with a split cylinder commutator? Two metallic rings are replaced with, yes, a commutator. The current, it changes from AC current into, yes, unidirectional pulsating current. So the AC current becomes unidirection varying current. What happens when the shunt in an ammeter is replaced with another of lower resistance? Okay, with respect to the sensitivity of the ammeter and the maximum current that the ammeter can measure. Okay, what happens to the sensitivity if the shunt is replaced with another, okay, of lower resistance? Sensitivity decreases, and this means the ammeter can read greater currents. What will happen to the reading on the hot wire ammeter in the opposite circuit when the key is closed? Okay, when the key is closed, what happens? Yes, we are connecting the second capacitor, and they are connected in parallel. So the capacitance will be increased, and when the capacitance increases, reactance of the coils decreases. So the current, yes, increases. So once again, since the capacity of the capacitors increases when connected in parallel, okay, so the capacitive reactance decreases and the current increases. So reading on the ammeter will be increased. Okay, what will happen to the reading on the voltmeter in the circuit shown in front of you when the value of the variable resistance is increased? Your attention please. Here the voltmeter reads the voltage across, yes, the resistance R. Okay, it is designed to measure the voltage across only R, the external resistance here. Okay, what about the voltage applied across this resistance? It is the product of the current and the resistance. The resistance is constant, so the current will determine what will happen to the reading of the voltmeter. When increasing the value of the variable resistance, the current decreases, so reading will be decreased. Okay, so the reading on the voltmeter decreases. Your attention please. Voltmeter here in this particular case reads the voltage only on the resistance R. What happens when the key in the circuit shown in front of you is opened? We've got neon lamp placed, connected across electromagnet. What happens? Yes, the lamp momentarily flashes. Okay, we want you to justify your answer. So the answer is the lamp momentarily flashes due to the high forward EMF induced by self-induction. What happens when the switch in the circuit is closed? Okay, your attention. of course, with respect to the readings on the 2 voltmeters, V1 and V2. Now, right now, before closing the switch, V1 reads, yes, the value is maximum and reads EMF of the voltage. V2 reads 0. So what will happen when closing? V1 will be decreased. It will be, instead of EMF of the cell, it will be just the terminal voltage. And since current will flow, so V2 will be increased. V1 decreases, but V2, yes, increases. V1 decreases, V2 increases. Okay, we want you, of course, to say what will happen to the readings of the 2 voltmeters. So V1 decreases, but V2 increases. What happens when a resistance of equal value to the fixed resistor is connected in parallel with it? Your attention, please. Here we've got, yes, a circuit in a state of resonance. Why it is in a state of resonance? Simply because XL is equal to XC. Inductive reactance is equal to 120 ohm. Yes, capacitive reactance is the same, it is 120 ohm. So we are in a state of resonance, okay? But when a resistor is connected in parallel to R, yes, total resistance, equivalent resistance decreases and current increases, but state of resonance will be unchanged. So the circuit remains a resonance state, but the current flowing in the circuit increases because the resistance decreases. What happens when the value of the variable resistance is increased? Also, this will not alter the state of resonance, but increase in the variable resistance will decrease the current. So the circuit remains a resonance state, but the current flowing in the circuit decreases. What happens? AC supply, okay, is replaced with the DC supply. If AC supply is replaced with DC supply, the capacitor will get charged, okay, and okay, quickly the current drops to 0. So the answer is the capacitor is charged, then the current quickly drops to 0. The following diagram, we've got another sort of questions, represents helium neon laser, okay? What is the value of the pressure inside the tube? It asks about the value of the pressure inside the tube. Of course, it's all easy. It is 0.6 millimeter Hg. What is the lasing medium in the device? In helium neon gas laser. What is the medium which gives us the light, the laser light we want? It is neon, of course, neon atoms. How is pumping accomplished in this laser? Okay, this could be accomplished by using high radio frequency waves or high DC voltage. Why is it important that the metastable state in a helium atom has a close value to that in a neon atom? Okay, this is very important question. Since the metastables of helium and neon are of very close values, so when a metastable helium atom and a ground state neon atom collide, the excitation energy of the helium atom can be transferred to the neon atom. Okay, so when a metastable helium atom collides with a ground state neon atom, what happens? Excitation energy is transferred from helium to neon atom. And this way, a population inversion situation of neon atoms is obtained. Also, talking about the same question, it is about helium neon laser. What happens if the two mirrors were removed? The two mirrors, okay, were removed. As a matter of fact, we won't be able to obtain laser light. The device cannot produce laser because the two mirrors are responsible for light amplification. And let me remind you with something here. The mirror with the lower coefficient of reflection enable laser light to emerge from the device. Okay? Also, what happens if the tube didn't contain helium atoms? Okay, this is very interesting also. Neon atoms, which are the lasing medium, could not be excited in their metastable state. Couldn't be, driven into, metastable state. They couldn't be driven into a situation of population inversion. Thus, the device would not be able to produce laser light. And now we've got another type of questions. We've got a diagram. The figure shows an excited atom already found in A2. Okay, and what about the question? Mention the different possible methods by which the atom may relax to the ground state. Okay, then mention 3 of the differences between the types of emission produced when the atom relaxes. Okay, first of all, the excited electron or excited atom, okay, relaxes to the ground state after its lifetime is over, and spontaneous emission occurs. This is the first possibility. Also, we've got another possibility. The excited electron is stimulated, is driven to relax to the ground state before its lifetime is over if a stimulating photon, okay, photon having energy equal to the difference between E2 and E1 passes by the atom and a stimulated emission takes place. And now talking about the differences between spontaneous and stimulated emission. Photons emitted by spontaneous emission have a wide range of wavelengths, so we call it polychromatic. Photons emitted by stimulated emission are monochromatic. They are of just one wavelength, of single wavelength. Another point of difference: photons emitted by spontaneous emission propagate randomly in all directions. Okay, they are divergent. But photons emitted by stimulated emission are coherent and propagate in one direction as collimated parallel beam. Spontaneous emission is not triggered, it's not caused by external influence. Okay, but stimulated emission is triggered by external influence. The light emitted by spontaneous emission obeys the inverse square law. The intensity, okay, of the light emitted by stimulated emission does not obey the inverse square law. Spontaneous emission is the dominant radiation in ordinary light sources, but stimulated, it is the dominant in laser sources. And now we've got another important question. It is about X-rays. The diagram shows an apparatus for the production of X-rays, used for producing X-rays. Show how the electrons are produced and suggest how they could be accelerated to the target. Okay, we'll take it one by one. Electrons are produced when a current is sent through the cathode. Okay. And what about accelerating the emitted electrons? Electrons are accelerated by applying high voltage between the cathode and the anode. Another item on the same question: how may the penetration power of X-rays be changed, be varied? How can we change it? Okay, by varying the accelerating voltage applied between the cathode and the anode. For example, increasing the accelerating voltage, increasing the potential difference between the anode and the cathode, increases the velocity of the electrons striking the anode. We call them bombarding electrons. And this increases the frequency of the emitted photons of X-rays emitted. So the penetration power of X-rays produced increases. Another item on the same question: how may the intensity of X-rays, intensity, not penetration power, be changed, be varied? Okay, intensity of X-rays can be changed, can be varied by changing the current flowing through the cathode. Increasing the current, increasing the cathode current raises its temperature, which in turn increases the number of electrons emitted from the cathode. And as a result, the intensity of the produced X-rays increases. Okay, another item: why is it necessary to use a vacuum tube? In other words, why the tube should be evacuated? Okay, if the tube weren't evacuated, the electrons emitted from the cathode would collide with the gas found inside the tube, and instead of colliding with the target, an X-ray would not be produced. That is to say, by evacuating the tube, the resistance encountered by the bombarding electrons is decreased. So evacuating decreases the resistance. What about the use of the copper block in the tube? Okay. During operation of the device, the temperature of the target, tungsten target, highly rises. The high heat conduction of copper improves the dissipation of heat. So we need to get rid of the heat produced. So we use copper because it is simply a good conductor of heat. So it dissipates the produced heat to the surroundings. What would happen if the target, and this is very important item, if the target in the tube was replaced with another target having greater atomic number? This will affect, line spectrum of X-rays. When replacing the target, line spectrum will be changed. And now we are replacing it with another one having greater atomic number. So X-ray line spectrum is changed. It would consist of shorter wavelengths. Okay. Another type of question: the following figure represents the intensity distribution of the spectrum produced by X-ray tube. Okay. Why are the sharp peaks on the diagram characteristic of the target? Sharp peaks actually, yes, are the line spectrum. So why they are characteristic of the target material? Line spectrum is produced when the bombarding electrons have enough energy to remove electrons from the inner shells of the atoms of the target. And what happens next? Okay, then electrons from outer higher energy levels drop to fill the holes, producing a group of distinct frequencies. Okay, another question, another important question. What is the relation used for calculating the wavelength of a characteristic line of X-rays? We want the relation used for calculating the wavelength of a line spectrum. Okay, the difference in energy levels equals E2 minus E1, and it is equal to h nu, and nu of course could be replaced by c over lambda. In this way we can calculate the wavelength lambda. And how are the photons having the minimum wavelength in X-ray continuous spectrum produced? Okay, they are produced, the minimum wavelength in the continuous spectrum is produced when a bombarding electron is stopped by just one collision. Is stopped by just one collision. And all its energy is converted into a photon. Energy gained by the electron in the electric field is EV. Okay, the electron loses all its energy into a photon having, yes, energy h nu maximum. And nu maximum could be replaced by c over lambda minimum. Another type of questions, okay. In front of you, we've got a diagram. Okay, a student disconnects the voltmeter in the circuit, removes the voltmeter, and connects in its place a battery and a switch. So the voltmeter is replaced by a battery and a switch. Okay, so we expect to form a motor. But when he closes the switch, the coil does not rotate as it should in a DC motor. What is the reason for this? Okay, what is the problem here? As a matter of fact, we've got two rings, so the coil will not rotate in one direction. It reverses the direction of its rotation twice a cycle, because the two rings always direct the current to flow in the coil in the same direction. In this way, we've come to the end of the edition. Thank you for watching. All the best and goodbye.